Hello students, in this video we will study what happens when hydrogen reacts with group number 16 elements. Okay, now we all know that when H, that is hydrogen H2 combines with O, we get water, that is H2O. So here I have already written we will be getting water, we will be getting H2S, H2Se, H2Te and yes H2PO. Fine. Now we should know what is the physical state of these compounds at room temperature. Water at room temperature, we all know that it is liquid in state. It is because water is having oxygen and oxygen throughout it is having smallest atomic size. Now when oxygen is having smallest, it is having smallest atomic size, okay, it is having high electronegativity. That is the reason that in case of water molecule there is a strong intermolecular H bonding. There is strong intermolecular H bonding. So students, it is because of this strong intermolecular H bonding, water exists in the form of liquid, that too at room temperature. Now you might be thinking, why only water is liquid at room temperature? Because I have told you it is the lone pair which is involved in the intermolecular H bonding. So you might ask me a question that in H2S, in H2Se, in H2Te, okay, we do have lone pair of electrons, and if they have lone pair of electron, why can't they form intermolecular H bonding? They do not form intermolecular H bonding, and why? I am explaining you this now, that why H2S, H2Se, H2Te are not forming strong intermolecular H bonding. As you all know, the criteria to form intermolecular H bonding is that element has to be highly electronegative, okay, and we know that as we go down, size of the underlined elements goes on increasing. So if their atomic size, if they have large atomic size, what will happen? The tendency, the capacity of the lone pair to get involved into the intermolecular H bonding will be very, very less. Now students, if H2S, H2Se, H2Te are not able to form intermolecular H bonding, what does it mean? It means that at room temperature, these compounds are gases. So you have to remember this, that H2S, H2Se, H2Te, they are gases. Now along with this, we also have to study what happens to the thermal stability of H2O, H2S, H2Se, H2Te, H2PO. First of all, what is the meaning of thermal stability? Thermal stability means that when you are heating that particular compound, how fast the bonds can be broken, the bonds can be dissociated. Now, what happens is, as you move down the hydrides of group number 16, please note, now I am speaking in terms of hydrides of group number 16. So as we move down the hydrides of group number 16, the bond length goes on increasing. What did I say? The bond length goes on increasing, bond strength goes on decreasing, and hence it is very easy to break the bond between metal, or it is very easy to break the bond between element and hydrogen. Now many of you might be thinking, what is this all about? I would like to explain you with one particular example. Fine. Now, I wrote here thermal stability, and I said it is the ease with which the bonds can be broken. Thermal means when you heat, if the bond breaks easily, it means it is thermally unstable. So, I said as we go down, the bond length increases. Now, I need to explain you that H2O, H2S, H2Se, H2Te. Okay, as we go down, students, what is happening? The size of the underlined element goes on increasing, isn't it? So, we know that this is the structure of water, distorted tetrahedral. Okay, but as I move down, the size of tellurium is going to be much more than oxygen, isn't it? So, when its size is more, then the extent of overlap with the hydrogen, this extent of overlap would be very, very less. Okay, overlap between tellurium and hydrogen would be very less. That is the reason the bond length would be more. So, as you go down, the central atom size goes on increasing, and hence the bond length, this bond length between the element and the hydrogen, bond length increases. That is the reason, students, I have written here BL, that is bond length increases. So, if bond length increases, bond strength will decrease. Now, it means as we go down, what is happening is bond strength is decreasing. So, if I talk for H2PO, it means it is easy to break the bond in H2PO, isn't it? That is the reason we say that H2PO is thermally unstable. Okay, because you give little amount of heat, the bond between polonium and hydrogen will break quickly. Okay, whereas H2O comparatively bond length is shorter, bond strength is more, and hence it will not break easily when the heat is supplied. Fine. Now, here it is written reducing character. So, we have to discuss what happens to reducing character. Okay, what happens to reducing character? Now, we have H2O, H2S, H2Se, H2Te and H2PO. Just now we studied that as we move down, the size of the central metal atom goes on increasing, bond length goes on increasing. Okay, as we go down, bond length increases, bond strength decreases. Hence, the bond between the element and hydrogen can be easily broken, when we go down. That is the reason we say that H2Te. Okay, this is radioactive, so we don't consider this. That is the reason we say that H2Te is the best reducing reagent amongst all these hydrides. Okay, so H2O is not having reducing character, but H2Te is the best reducing character because bond length is more. So, we have finished what is the reducing character we have discussed. Now, the next part, if you see, it is written as volatile character. What do we mean by volatile character? Volatile means which can easily evaporate. For example, we are having nail polish remover, okay, wherein if you keep the lid open, that nail polish remover, that is acetone, will evaporate. Now, we have to discuss among these hydrides, okay, what happens to the volatile character. Ideally, if you see that, I have written in previous stages also, I have written that H2O is a liquid, isn't it, and rest all are gases. So, if we consider this particular parameter, then H2S would be having more volatility than water, H2SE will be having more than H2S, H2TE will be having more than H2SE. So, according to whatever we have studied so far, we are assuming that in this way the volatility, the volatility increases. But students, this particular trend is wrong. So, what is correct? I am telling you that with the reason. It is found that among all the hydrides, only and only H2S is volatile. Why? We will study one by one. Why H2S is volatile whereas other elements are not. Now, first we will discuss why water is non-volatile. I hope students you can answer this question easily. Water is non-volatile because at room temperature water is having strong intermolecular H bonding and hence water is non-volatile. Now, we will consider H2SE and H2TE. Students, as we go down the group number 16 hydrides, what is happening is the molecular mass goes on increasing, isn't it? When any substance is heavy, it is not possible to lift that substance. Similarly, H2SE molecular mass is more than H2S, H2TE molecular mass is more than H2SE. So, because the molecular mass increases, molecular mass increases, they do not remain volatile and hence we say that they are non-volatile. Now, H2S in comparison to selenium and tellurium, here sulfur is able to remain volatile because its size is not, its size as well as its atomic mass is not that greater than Se and Te. So, you have to remember why water is non-volatile, because it is having strong intermolecular H bonding, and H2Se and H2Te they are not, because they have more molecular mass. For the hydrides of group number 16, let us discuss the hybridization also. Now, since already once I have drawn the structure, that is oxygen is having two lone pairs like ears of the rabbit, and here we are having hydrogen atom. So, we know very well that there is a repulsion between lone pair and lone pair of electron, and hence we say that there is a repulsion between these two. Also students, we know there is a repulsion between bonded pair and lone pair. There is also repulsion between bonded pair and bonded pair, because of which the structure is distorted tetrahedral, and hence we can also say it is having angular geometry. Now, the hybridization is sp3 for all of them. Fine. Now, since we have studied hydrides of group number 16, let us quickly learn hydrides of group number 17 as well. So, here we have reactivity of group number 17 with the hydrogen, and you can guess that we would be getting HF, HCl, HBr, HI, and this, let us leave it like this only because it is radioactive, it may not follow all the rules. Fine. So, this is the formula. Next is the acidic strength. Now, students, we have studied in group number 16 as well that as you go down the group, what happens? Atomic size goes on increasing and hence bond length goes on increasing and bond strength goes on decreasing. It means fluorine smaller size than chlorine, having further smaller size than bromine. Iodine is having larger size. Iodine atom is the largest atom in the group 17. So, the bond length in case of iodine will be maximum and hence bond strength is very less. It is having weak bond strength. That is the reason it is very easy for HI to release hydrogen, and hence we say that Hi is a strong acid in comparison to HF. So, here it is weak acid. So, I have shown you the trend that as we go down the group hydrides of group number 17, their acidic strength goes on increasing. Now, here we have bond length and bond strength, which I have already discussed, that bond length goes on increasing, bond strength goes on decreasing. And now we talk about reactivity of hydrogen with the noble gases. Noble gases, children will know that they are inert in nature, they will not react with hydrogen. So, we do not have hydrides of group number 18. I hope you all have understood this video wherein I have discussed the hydrides of group number 16 and 17. Thank you.